Welcome back. So, in today's video lecture, we will look at the derivation of Young's equation, right? So, last class we looked at various measurement techniques. Okay, we looked at using the capillary method as well as the Wilhelmina plate method and maximum bubble pressure method. We have shown that how you can measure surface tension if theta is known, right? So in today's lecture, we will look at spreading of droplet on surface. So this is important when you want to understand the surface property. Okay, whether a droplet, a liquid droplet will spread nicely on a surface or not can be easily assessed using what is known as by knowing the contact angle, but we can also use the relationship, the equation proposed by Young's, right? So we'll see that part in today's lecture. Okay, right. We'll move, let's begin our lecture, right? Yeah. So, in today's lecture, we will look at how spreading of droplet on surface, right? Or how the surface will influence the spreading of a droplet, right? So, let's say we have surface and we want to understand whether a liquid droplet, if I place it on the surface, will it have a tendency to spread or will it have a tendency to retract, right? So wetting or de-wetting characteristics of surface can be easily quantified or assessed using what is known as Young's equation. So we are going to look at the importance of this equation, right, in various applications. For example, in this equation, we are going to look at the competitive forces, right? Surface energy, various surface energies that exist when we spread liquid on the surface. For example, gamma Sg, right, which is associated with surface and gas phase, which is exposed to, and gamma Sl and gamma Lg, right? So these three competitive surface energies will decide or will dictate what is going to be the contact angle of a given liquid. Now, what is the importance of this study is, let's say whenever you want to understand, let's say for the application of farming and pesticide, where you use pesticide to promote the plant growth, there we want to know whether the pesticide which we will spray on the leaves or branches of tree will spread nicely or not, because here the spreading is very important, right? So in this case, you want the surface to be more hydrophilic in nature, okay, based on which you will design the formulation. So the liquid will spread on the surface, right? On the other hand, you want to make, let's say you want to make waterproof fabric. In this case, you want the surface to have more water repellent property, right? Usually it should exhibit the contact angle with the water above 150 or 160 degree. In this case, you would expect the surface to behave like a super hydrophobic, right? So, in these applications, one would want to quantify the surface, like whether it is naturally hydrophilic or hydrophobic or not. If not, one would want to modify the surface so that it can be used for the given application, right? So in this case, we will look at one important equation proposed by Young himself. So before we begin, let's understand the assumptions proposed by Young, which is nothing but this equation can be used, right, only when equilibrium condition is considered, right? For example, in this case, when we place a droplet, okay, we are not interested in measuring the theta instantaneously. Rather, we are interested in measuring the equilibrium contact angle. So, which means that equilibrium condition should hold, right? So, equilibrium condition is attained. So, we assume that the droplet has attained equilibrium condition, right? Okay. The second important assumption is the surface should be smooth. So, must be smooth and homogeneous. So, which comes to say, this equation is not valid for surface where it has roughness, right? The surface with roughness and chemically heterogeneous surface. So, in these cases, this equation is not applied, right, or applicable. And third one is no imbibing, or surface should not absorb any liquid, okay? Should not absorb any liquid, or no imbibing conditions. Okay, so this should revive. Only then we can say that this equation is can be used, right? With all these conditions met. Okay, so let's begin how we can calculate or understand the contact angle, which is three-phase contact angle. Let's look at the sessile drop. For this case, we say we place a droplet on the surface. Okay, the theta that we define is nothing but the theta established on the liquid or solid is nothing but theta, which is also nothing but three-phase contact angle, because at this junction, all three phases exist. For example, solid, liquid, gas, all three phases exist. That's why we call it as a three-phase contact angle. Okay, so what is there are three governing forces which dictate the contact angle, which decides what is going to be the theta on the surface. For example, when you spread low energy liquid on high energy surface, it will spread, whereas when you spread high energy liquid over low energy surface, it will not. So this is actually dictated by the surface energies. Okay, as I explained already, there are three competitive forces which exist in this case. They are nothing but gamma Sg, okay, which is because of association with the solid and gas, and gamma Sl. So this gamma Sl is this part. This part is nothing but gamma Sl, whereas this is nothing but gamma Sd, and this is nothing but gamma Lg. Okay. Okay. So if you look at this equation, let's say when we spread droplet, the components, the components of gamma Sl plus gamma Lg, okay, cos theta. This ensures that the droplet is spreading. On the other hand, gamma Sg, which will try to oppose the spreading, okay, because this won't expose maximum exposure with the gas, but when you try to spread liquid, this particular force will try to oppose it. That's why there are two competitive forces in this case, there will be two counteracting forces. One will be sum total of gamma SL and gamma LG cos theta. The other one will be gamma SG, right? So why this cos theta coming into picture is because LG is the gamma liquid which is associated with the gas, because it establishes surface with some angle that is called theta. There will be the component of the resulting component will be gamma LG cos theta, which you can obtain through a simple geometric relation, right? So this is nothing but so this will yield because there are two competitive forces. So this will yield the equation at equilibrium. What will happen is both these counteracting forces balance each other. So it will you will get an equation in this way, which is nothing but gamma SG should equal gamma SL plus gamma LG cos theta, because this force is acting in the positive x direction, whereas gamma SL and LG acts in the negative x direction. So at equilibrium, both should be equal. So one would get equation of this kind, which is nothing but gamma SG is equal to gamma SL plus gamma LG cos theta. One would also calculate cos theta, by knowing gamma SG minus gamma SL by gamma LG. So in this way, you can calculate what is theta. Okay. So this Young's equation can be used to quantify what will be the theta on a given surface, right? Yeah. So one can derive this equation alternatively also using the change in Gibbs sphere energy equation, which is nothing but energy after droplet attend equilibrium and energy from the initial configuration. So if droplet has to spread, right, then the energy associated with the final configuration should be minimum compared to the initial, right? So in this way, you can say that the process is spontaneous. So what we can try to show is, let's say initially we have droplet. When you place droplet sit on the surface at time t equal to 0, but after it is after it reaches the contact point, it will try to spread, right? And then at equilibrium, and it will spread until it reaches the equilibrium, right? So this is what we know. So let's understand that this initial and final configuration will look like this. Okay. So, okay, yeah. So this is actually initial, and this part is final after spreading, right? After it attains equilibrium. Let's say if you assume that this process is spontaneous, now how we will arrive at this equation is what we are going to look at. This alternative way of obtaining this equation, right? So if you look at this, this surface, right, is now covered by gamma SL, which means that previously this was occupied by gamma SD. Now that surface energy is lost because that is replaced by gamma SL. So gamma SD no longer exists, right? So we know this gamma SL, and at the same time, the area associated with the gamma LT has also increased because of the spreading, right? So if you want to understand this increase in area, right, one can calculate using the geometric relation, which is nothing but, in this case it is nothing but delta. If I say this is nothing but delta L, if I say this part, this length, change in length, nothing but delta L, then the increase in area due to the spreading of droplet is nothing but x is equal to delta L cos theta. Okay, so this part also we know. So because of the spreading, the sum of the gamma Sg part is replaced by gamma Sl, so that gamma Sg is lost. At the same time, because new energy is created, new surface is created as the droplet spreads, you will also have change in area with respect to due to droplet spreading associated with the gamma Lg. So you will have a component there, gamma Lg delta L cos theta. So we will now write these things in detail in the form of equation. Let's say delta dg is nothing but final is nothing but I know gamma SL because gamma Lg is replaced by gamma SL. So this part is gamma SL. So gamma Sg no longer exists. So it is nothing but gamma SL into delta L. So if you look at this, gamma SL into delta L is nothing but the force, simply nothing but the force, because it will be Newton ultimately. So to make this equation consistent, we will divide this change in Gibbs sphere energy with respect to unit of width, so that the equation is consistent throughout. Now, not only gamma SL, the final configuration is not only gamma SL, but it also has gamma Lg into delta L cos theta component. Because of the spreading, because it establishes some angle with the solid surface, okay, and you can obtain using the geometric rule. So based on which you will get gamma SL into delta L plus gamma Lg to delta L cos theta. And my initial configuration, I mean, when I spread droplet, when it just touches the surface, hits the surface, at the time, what was existing before spreading was gamma Sg itself. That is what I am going to write in this case, right? Which is again multiplied by delta L. Because that portion, gamma Sg into delta L, is what going to be replaced by gamma Sl delta L, right? After spreading, right? Yeah. So now we know at equilibrium delta G dg is nothing but 0. So we can simply have gamma Sg into delta L, which is nothing but gamma Sl into delta L plus gamma Lg into delta L cos theta. So if I divide both the side by delta L, I will simply get gamma Sg is equal to gamma Sl plus gamma Lg cos theta, or cos theta is nothing but gamma Sg minus gamma Sl by gamma Lg. So you can also alternately prove that Young's equation is nothing but cos theta is equal to gamma Sg minus gamma Sl by gamma Lg. Okay, so we will, based on this equation, we will also try to solve a tutorial exercise in this lecture itself. Okay, now we will move on to the tutorial part. So the tutorial part, we have got a couple of equations. Okay, one is based on the capillary method that we saw in the previous lecture, right? Capillary method using the previous lecture, and the other one is based on the Young equation. Sometimes it is also known as Young-Dupre equation. Okay, you will find in many textbooks it is called as Young equation, but it is also sometimes known as Young-Dupre equation. Okay. So in this exercise, we are going to calculate the rise of ethanol. Okay. Basically nothing but the height of the liquid column is what we are going to measure. we know the relation, right, that we obtained using the capillary method, which is nothing but 2 gamma cos theta by RC, right? This is what we, the relation that we obtained using the derivation that we saw in last lecture, okay? So delta P is nothing but H into rho into G, whereas on the other side we have 2 gamma cos theta by RC. RC is the capillary radius, right? So we know, so 2 into gamma, so gamma here is Lg itself, which is given here. The gamma here is Lg itself, right, which is already given here, which is nothing but 22.4, or you can say 0.0224, right, Newton per meter. Cos 0 is 1, so we don't need to worry about cos theta component. Then we have rho, density is given, which is nothing but 790 kg per meter cube. And then we have gravity is nothing but 9.81 meter per second square, right? So if you simply, so this is nothing but h, right? So if you simplify this, you would get ultimately approximately 57 mm, okay? So the capillary, height of the capillary, rise of the height of the liquid column in this case, in this problem is 57 mm, okay? You can check that, right? Yeah. So the next exercise is going to be using the Young-Dupre equation or Young's equation. Can we calculate what is the wetting angle of alumina, okay, by a nickel-based liquid, okay? So some of the data is given already. So we know gamma aluminum gas. So gamma SD is already given, which is nothing but 0.9 Newton per meter. We also know gamma LG, which is nothing but 1.72 Newton per meter. And we also know what is known as gamma SL, which is nothing but 2.3 Newton per meter. So we know what is cos theta, which is nothing but gamma SD minus gamma SL divided by gamma LG. So if I simply substitute all these values here, this will be 2.3 divided by 1.72, one would get theta, which is cos inverse of this whole component, which is nothing but theta is equal to 144 degrees. So it is highly hydrophobic. The surface is highly hydrophobic. So comment on the wetting of liquid. So you can say that it will because theta is greater than 90 degree. Since it is hydrophobic, in fact this is almost it is, you can say that theta is very high, so it is almost like super hydrophobic surface. So you can comment saying that the liquid will not wet the surface so easily, right? So we can stop here. We can continue from the next lecture. Thank you.